So last time we've been discussing on membrane crystallizers, and today I was telling you we will discuss of another unit operation. Also, this one is not yet developed on large scale as membrane distillation or the other one. However, is one of the example of how you can today, using membrane engineering, try to redesign basic unit operation of process engineering. Condensation is present everywhere today, and very often, if you analyze in terms of process intensification index, that means how efficient are these operations using this new concept of process intensification, they are not efficient at all using this kind of logic. In fact, following this kind of concept, in Europe, we had recently a research program involving industrial world and involving a lot of researchers from different European countries. All the European projects are multinational, looking to the possibility to grow in some other areas the problem of water purification, not just brackish water or seawater that everybody is familiar with, but for example, trying to use all the water present in the flue gases that most industrial production are producing in a quite significant amount. To give you some example, we were looking that if you are looking to the coal fire plant or to the cooling tower or some paper production, etc., the number of a cubic meter of wastewater that you evaporate continuously and you lose in the atmosphere can be quite significant. And in many industrial sectors, all these companies are present, and per hour, you can see here, in the coal fire plant, you produce 150 cubic meters of wastewater. And sometimes this wastewater is also contaminated, so there is a problem that you have to try also to clean this water, etc. That's why in Europe we had the possibility to develop one project that was called CAPA, you'll see, in which researchers from all around Europe have been trying to compare the possibility of a new methodology based on basically on membrane system with the traditional one. The industrial people were making the cost analysis and the technological evaluation, and the researchers were trying to utilize membrane system for solving this problem, which is on the one way an environmental problem. In part, you can also reduce the air contamination. On the other part is just your recovery water, that for company located, for example, far away from the shore, far away from the sea, or in some part of the world, in Africa, in some South Africa, for example, was a partner in this project, or in some other country in Africa, can be quite important. It seems we learned that if you can just recover about 20-25% of the water that they are losing continuously, the company can become independent from external water supply. So if they have a continuous recovery of the order of 20-25%, they don't need a continuous supply from the river, from the lake, from the sea, etc., etc. So quite interesting. The way of doing is the name of the project was CAPA, water capture. And the way to introduce membranes was double. Part was just to use dense membranes. We have not been discussing during this course about the dense membrane operation, which is very familiar, and we will discuss eventually in the fall course. But as you know, gas separation, CO2 capture, hydrogen production and the purification, and oxygen, nitrogen separation can be done with dense membranes. And in some cases, these are dominant technology. All of the nitrogen produced today, non-cryogenic, that means for certain dimension of the plant, when you read on the nitrogen you are buying, non-cryogenic, is membrane system. There are membranes in which you can separate easily nitrogen from oxygen, competitive with traditional cryogenic system. So non-cryogenic basically means today, in some cases means also PSA, but normally today means membranes. So you can use dense membranes for the same story, dehumidification. In our case, and what we want to discuss is to use a new technology, membrane condenser. So membrane condenser is, and that is just the concept, is nothing more than having at the exit of your flue gases from your chimney a system, some membranes, which must be able to avoid liquid water going through and leaving only gases going through. And we learned that that can be done, because if we are putting here some hydrophobic microporous membranes, and we find a way that this water that is present in a vapor phase will become a liquid water. That means if we condense the water, that's what we expect to do in a condenser, we can have that the water will not penetrate and only the gas left, nitrogen, oxygen, CO2, will go through your membranes. That's just exactly similar to what we have been discussing the past lectures, in which we were just warming up liquid water on the same membranes, making the liquid water vapor and moving the vapor across. Now what we have to do is just the opposite. We don't want to have any liquid water going across here, so we condense the water and only the gas will go through. For condensing the water, what we have to do, instead of warming up, as we were doing membrane distillation or the membrane crystallizer, so instead of evaporate the water, we have to condense the water, which means we have to cool down the membrane surface instead of cooling up. But basically, all the other, we are changing the system in terms of operating parameter, but the concept is very similar. So that is the flow sheet of the system that you can imagine. You can have a dry gaseous stream going across your membranes. You can condense the water, and you can recover this water, and you can recycle to the plant or make the use that you're looking for. Is a relatively interesting, simple concept as all membrane operation. A lot of problem exists for making these plants huge and utilized everywhere. However, a lot of progress has been done, and people are working today for making the system working. And you can see here you have a supersaturated flue gases that has to go on your microporous hydrophobic membranes, and hydrated gaseous stream will go across, or hydrated at the level that you are able to remove the water. So you have 20%, 60%, 80%, what is necessary, and the condensed water can be utilized. In both cases, what is interesting, what we were trying to do is not only to condense the water, but to condense the water in a system that has to be, first of all, consistent with the basic principle of process intensification. So low energy consumption, flexible, easy to make automatic, with no other trouble, easy scale up, scale down, modular, basic property of membrane operation. And in the meantime, something better. That means something that normal condenser cannot do. And this is the most important part of the story, because we will see that if you do this kind of system, in principle, at least at the level in which we are working today, in pilot scale, etc., you don't only condense the water, but you can condense the water, you can control the level, the percent of contaminants which are present in the flue gases, and depending from which kind of reuse you want to do with the gas stream or with the condensed water, you can decide which percent of contaminants has to be removed. In some cases, some of the contaminants can be useful and necessary for going back in the process. And so in this case, you will have to keep all the contaminants present in your liquid water. In some other case, the contaminants you don't want to have, because this water, for example, is drinkable water you want to use for different motivation. You don't want to send the water back in the process, so you have to remove this. Not easy to make with a normal condenser. Normal condenser don't do this job, but just they condense, and that is That's all. If you have to make any purification, etc., will be later on. In this case, you can combine the two things. Remember that one of the interesting requests of process intensification and opportunity with membranes is the integration of different functionalities in one unit operation. We will discuss a little bit next week or today if we can about membrane reactors, for example. Until now, we have been only discussing single units. Reverse osmosis or nanofiltration, etc., single process. In nature, a lot of processes take place where more functionality are together. In our membrane, in our body, we have membrane that separate, convert, transmit. No, they give you signals, they make different functions. Membrane operations are starting to do the same. So in some cases, as this one and as membrane reactors, we have more than one functionality. Here we have to condense, and we want to utilize the quality of the water for specific motivation, and this can be done. If you try now to predict if the system works, it's also interesting. Always a little bit is a simulation, so you have always to check your numbers, but you can just try to analyze what is happening in your system. You just have a condensation, and you have to calculate, for example, which is delta T, which is a level of cooling down necessary on your membrane surface to have all the water coming in vapor phase condensed on the membrane surface. If you do this kind of calculation, you have to calculate a different relative humidity present in the gas stream coming out. You can assume 100% humidity in this case, or you can assume 80%, 90%, depending which kind of flue gases you will have. And for each kind of, for each temperature at which you are working, you can calculate the percent of water you can recover as function of the temperature on the membrane module, on the membrane surface. So you just have your delta T. And you can just, you have this kind of behavior, and you can see that which is the delta C necessary for obtaining a certain level of condensation, 50%, 20%, 80%. This is just simulation. It's just calculation that you do on the computer, just analyzing your system, not too complicated to be done. So you have that increase in the temperature, assuming constant relative humidity. The amount of water that in the vapor phase is, water vapor in the vapor phase is higher. And for if you want to have the same percent of recovery, for example, 50%, you need the higher volume of water has to be condensed for requiring a heat duty, which is the amount of energy power that you have to give higher. That is the same calculation here. You can replot from here total power for each water recovery, and you see that basically that the total power necessary is increasing the water recovery that is necessary, and that's exactly what you expect. What is important is to see if this kind of prediction will be consistent with the reality. By the way, we will discuss a little bit today what is happening for what concerns the membranes. In each discussion we had until now, we have never been discussing about the membranes, basically, or a membrane is the core of the system. I will try to give today some links between the property of the membranes, what we have to do to realize membranes with properties which are appropriate for the kind of requirements that we are looking for. For example, level of porosity, level of hydrophobic character, etc. This is a typical case in which we have to realize, for doing this kind of operation, new membranes, and you have at least a new for trying to have appropriate membranes for this kind of system, and they will be basically, in this case, most part of them prepared by amorphous perfluoropolymers. That is the one that we have been already mentioning a couple of times, talking about membrane dissolution, etc. But in the case, for example, of a membrane condenser, we are starting to produce also membranes appropriate for this kind of operation. As you know, today, in all these membrane contactors, we don't have specific membranes. The membranes we are using are the ones produced for microfiltration or for other application. And eventually they can also be utilized for microfiltration and membrane distillation. More and more, we have to learn that if you want to utilize a membrane for membrane distillation, membrane crystallizer, membrane condenser, the one that you are using for microfiltration are not the best, the most appropriate. And we already mentioned something. Today we will try to make some analysis similar. That is the case in which we have been working with some new polymer, for example, with Alar, and in which the roughness of this surface is different from the initial one. We have a roughness of the surface of the upside, which is lower than the surface bottom side. And sometimes it was the opposite. But in this case, that can be interesting when you can control the roughness of the upside or bottom side, because the amount of roughness is related to the temperature polarization phenomena. Increasing roughness, you can reduce temperature polarization profile. It's again a turbulence promoter, basically. And this is one of the things that we like to do. But anyway, let's go back to the data. Here you can see the water, the water recovery, again as a function of the temperature of the membrane module. And this is done at different axial velocities. So what happened here, that you are changing basically the contact time of your flue gases on the membrane surface. So you are changing the possibility to condense or not condense, and also to the possibility to not only condense water, but to condense the contaminants present in the water. What is happening here, that the amount of water recovered as a liquid in the retentate increase as much lower is the temperature. If you are decreasing temperature, condensation is increasing, and the fraction of water recovered is higher at the lower feed flow rate. That means you are increasing contact time, and you are just increasing the amount of water recovered. And that is just, and on the contrary, for high feed flow rate, the amount of water contained in the feed is much higher, and the membrane area of the module is not enough to retain the most of the water. So these are all experimental results which are quite consistent with the expectation, basically, and they are quite consistent with the prediction that were done before, just in simulation. Here he had the different feed temperature was 65 degrees centigrade, and again here you have different flow rate, and again water temperature. The water recovery is functional temperature of the module, is just consistent with all this kind of expectation. You can just now to try to analyze your new unit operation in terms of this, in the logic of process intensification. For doing this, we try to introduce what they are called also this process intensification index. For example, the one that we discover here is quite interesting, is the ratio between the axial flow rate and the membrane surface. This is a typical PI index that is useful to understand and to predict the overall performance. So here what is plotted here is the water recovery, percent of water recovery as a function of the feed flow rate, but you're just trying to recalculate the data as a function of this axial flow rate divided, the normalized to the membrane surface. And you can see here that the water recovery is less sensible to the feed flow rate at, for high delta T, when delta T is significant high. And here is 55, and this is 65. A high delta T facilitate the water condensation and compensates the low effect of the condensation due to the lower contact time. So that is the two parameters can just be integrated. On the contrary, if delta T is low, the contact time is a fundamental parameter, and it should become the rate determining step. So there are situations in which the temperature is playing a very important role, and that is when the delta T is low, and the other one in which is less sensitive. Basically, the two parameters which are controlled in the process is just the membrane surface. Increasing membrane surface, you are increasing contact time, basically, and the delta T difference between the temperature of the flue gases coming out from the chimney and the one you are able to realize at the membrane surface, which is the most important because that's the cost of your, the energy cost of your condensation. Cooling down the membrane surface is basically all the energy that you have to spend for realizing your plant. That is the most important parameter that we have to consider. You can see here that in the worst condition, that means higher feed flow rate of about 25% of the water contained in the feed is retained, which is more than what was the expectation. The people sponsoring this project, they were happy if you just realized 20%, because 20% is giving the possibility to become independent. And with the delta T of basically 8 degrees centigrade, which is relatively not too high, you can recover 25%. If you want to recover 60%, much more than necessary, you can just have to realize a delta T of 15 degrees centigrade, which again is, you have to, that is the real cost of the process, which is not too easy. Remember that we discuss, when we are talking about membrane distillation, we have been discussing about already 4 different kind of configuration. Direct contact membrane distillation, or vacuum membrane distillation, gas strip, stripping gas, air gap, etc. So membrane distillation engineers have been already redesigning. Nothing of this kind has been done or published until now in this system. Everything that, all this situation here at the moment is just done by cooling down. In our case, we have the module, and we put the module in a control temperature chamber, and we change the temperature of the chamber compared to the temperature of the flue gas, and that is this way we create delta T. But this is action number 1. You can realize the same delta T in many different ways. For example, you can cool down downstream your membranes on the other side of the condenser. You can cool down upstream by putting in a lower temperature chamber, or you can try to use a stripping gas, nitrogen, that you cold nitrogen running on the membrane surface, which can be interesting because in this case you can facilitate the removal of the water that you are condensing. So also in this case, the way in which you can realize the delta T in the system and to operate your condenser are much more than single one. And there's a lot of work to be done, and people and our students are doing this to identify which one of different configuration in terms of temperature polarization, in terms of contaminants removal, etc., is the most appropriate. So there's a lot of work to be done, and here on the 10th floor, we are just studying membranes that can be more appropriate for this kind of system. For example, membrane which can have a well-controlled roughness for controlling temperature concentration profile, or high level of hydrophobic character for keeping these things has to be cheap but stable. You don't want to change in a condenser. Things has to move for daily, 24 hours per day, every day for years. So you need some material with appropriate properties. Again, here is a typical example, some new amorphous perfluoropolymers which are under investigation. And in this case, what is interesting for the moment is just to show that you can change significantly the contact angle between one phase and the other one, upside and bottom side of your membranes. That means these are flat sheet at the moment. That means bottom side means on the glass plate on which you are condensing, and the other one on the upper side. This material is strongly hydrophobic. You can see here that you can have on the bottom side about 130 contact angle, and we learn what means the contact angle, 140 in this case, and 90 on the other side. If you just try to analyze now this kind of system and understand which one of the two phases is the most appropriate for in terms of temperature profile, etc., this is material that you can handle and try to realize for this specific kind of application. Some of these membranes are still PVDF. Some other one, what we call a new polymer, is HALAR. So you can be from is much more stable in terms of hydrophobic character than PVDF, and that's why we are looking to this. It's interesting that you can have not only interesting performance in terms of hydrophobic character and stability and possibility to change significantly contact angle between upper part and bottom part, but we have also interesting mechanical properties. And mechanical properties are playing a significant role on the lifetime and the aging of your membranes. You can see that compared to PVDF, the young modulus, elongation and break are much more interesting than the PVDF itself, and PVDF is an interesting material. Going back again to the hydration experiments, this is again some comparison now between the new membranes and the new polymers and the traditional one. At this level, nothing really exciting is coming out, because as you can see here, this is what we have. It's just water recovery as function of the feed flow rate again, and basically the system at a different temperature of the feed and the humidity, they are not very different one from the other. Normally, these new polymers are better, but there is no dramatic increasing of performance. This is because more work has to be done, but basically, this is just the water recovery as function of feed flow rate. It's not lifetime or hydrophobic character or contaminant concentration. So if you enlarge this kind of comparison, introducing new parameters related to the process intensification logic, our expectation is that this comparison will be much in favor of the new polymers. But that's something that you will read in the new publication that will come out. And the performance of the module using the new polymer and flash sheet are comparable at the moment with the PVDF hollow fibers, which are some of the commercial ones. So nothing really exciting, but interesting. You can start to make some more general comparison, and this is interesting, between this very new membrane operation as the membrane condenser with all the traditional system. And this is interesting because if you now make a good comparison, you will see that in relation to the traditional system largely used today as a liquid sorption, for example, or also as cooling with condensation, the value that this very relatively new technology where a lot of improvements are expected, etc., is in some case quite interesting. This $4 per cubic meter here is 1.5 roughly, or almost 2, and or similar and competitive with the other membrane system, the dense membrane system. There is an interesting factor, however, to consider, which has not been considered too much in the cost today, using again membranes. If you are familiar with the membrane problem for gas separation, most part of the membranes we are using today for gas separation, they have a problem of stability, of fouling, but specific fouling. That means in the gas stream, sometimes there are contaminants. If you want to purify hydrogen coming in a refinery, there is a lot of chemicals starting from sulfide, etc., that you have to remove. Otherwise, the stability of your membranes is not good enough for long time operation. That's the case that has to be considered. If you are just working on water in your gas stream, no big problem. This membrane can be stable, the dense membranes. If you're starting to work with, not in real life, when there is sodium, hydrogen sulfide or fluoridic acid, we have in some cases, etc., you must be careful because some of the membrane that you are using, some of the polymer, for this case, PEBAX or some polyamide, etc., can have trouble with in long range time. These polymers are expected not having this problem. Remember that membrane operation for gas treatment are exactly same mechanism than reverse osmosis. Solubility, diffusivity mechanism, you will learn. It's just you have your chemical that will be solubilized in the polymeric phase and diffuse, which means the chemistry of the material is very important. And the chemistry of this material can be modified, can be affected by the quality of the contaminants present in the feed state, in the feed solution. When you are working with microporous hydrophobic, and we discussed already microfiltration, the chemistry in the first approximation is not very effective. Here, what is important is the configuration and the morphology of the material. There is a big pore, everything has to go across, there is no chemistry involved, no adsorption, no solubilization, and just viscous flow across, or Knudsen flow across. So the chemistry is much less important, and in particular, these materials are perfluoropolymers, which are stable to most part of the contaminant, much more stable than the one we are using here. So that's why this kind of methodology can have, is becoming more and more of interest in our personal opinion. Anyway, to conclude this, if you make this kind of preliminary analysis and you compare the condenser based on membrane with this other one, there is no reason for not telling that you have to try to work more and more and try to optimize it the best. This is the most important part of the story that I show you already probably, because now if you could try to predict what is going to happen when you just will not only condense the water, but you want to try to condense the water of a certain quality, depending from the kind of feed you have, etc. With the membrane condenser can be done by controlling the cross flow, the feed velocity on the membrane surface. Or better than this, to control the parameter I was showing before, that means the feed velocity divided for the membrane surface available. You can see here that if you have ammonia or fluoridic acid or SO2, etc., present in the stream, you can changing the cross flow velocity, and you can just significantly change the concentration. You can go through a maximum, so you can minimize or you can maximize the level of some of the contaminants present. In some cases, you want to eliminate because they can be dangerous for the final utilization of the liquid. In some other cases, you want to recover as much as possible because you want to reuse eventually in the process itself. Normal condensers are not doing this. Membrane condensers are doing this. And if there is, no, it's not here. If you just do this kind of analysis in a more recent study, you will find literature for the SO2, which is a very important case. If you make now this modeling, these are simulations with the experimental result, you will find a very nice agreement between the expectation and the experimental result that you can obtain, in particular the one we have now as the one with the SO2, which is one of the major contaminants that are present. We are not supposed to talk too much about the membranes, how to make the membranes, and the membrane that we are going to use in this process as term of manufacturing. However, I think we have to start to realize how important is to produce membranes appropriate for the final scope that you are considering. So you don't have to buy membranes or to make membranes. You have to make a membrane having clear in mind which kind of application is the one for which you are working. And they become very often, you cannot use your membranes for RO in a nanofiltration or in one of the separation. If your membranes have been studied to separate CO2 from nitrogen, the probability they are also good for one of these operations is not very high in some case. So that means more and more you have to try to analyze which are the parameters which are controlling the system. That's why more and more we have been talking during these lectures about polymer that until recently were not very much utilized for making membranes, as the fluoropolymers. Some of you are already working just in producing membrane based on fluoropolymers, and these materials are very important in some application as microfiltration and ultrafiltration, PVDF typical example. But more and more, they are becoming more interesting for this new operation. All the operations we've been discussing, membrane distillation, membrane crystallizer, membrane condenser, and some that we have not been discussing, but membrane emulsifier, membrane dryers, by the way. When we will have time, one of the new operations you will find in literature is to produce dry powder, which is quite important in most parts of the final formulation. One way to remove completely water from powders with avoiding this formation of clusters of big agglomeration of the powder, etc., is again a membrane operation, which is becoming of interest today. However, in all these operations, you will see that fluoropolymers, and PVDF is a typical member of this family, are becoming crucial polymers, to the point that today, in different parts of the world, particularly in this part of the world, you will have a company building a new factory for producing fluoropolymers. And not just traditional normal PVDF, the one that one time was just PVDF. Today, more and more, you can have copolymers of the same PVDF or new polymer very much related. This typical example, the PVDF is this typical formulation, and this is Teflon, the tetrafluoro, and this basically what we call also Teflon. This PVDF is only 2-fluorine, 2-fluoro group here. Other ones are coming today. For example, this is called ALAR, and the ALAR was not very utilized in membrane operation still today. There's only one company in the world probably trying to make membranes with ALAR, but it's quite interesting in the logic of the discussion that we've been doing the last hours, because the level of hydrophobic characters of this polymer is much higher, is better than the one of traditional PVDF. So if you are looking, keep in mind that very often when you're producing membrane in PVDF, you produce as they are, and after you have to transform these membranes from hydrophobic in hydrophilic. If you want to use PVDF as microporous in microfiltration or in ultrafiltration, after producing the membranes, fibers or flat sheet, you make some special treatment with ethyl alcohol and other things for making this material hydrophilic. Today, the world is changing. You have to work to make this material eventually more hydrophobic, or change the material and produce another one which is more hydrophobic than PVDF. So when we will read something about ALAR, one of the first sentences will be more hydrophobic than PVDF, and no reason to make hydrophilic. Go back to PVDF eventually. These polymers are already being utilized. This CTF, this ALAR, eventually has a potential also in pervaporation if you make dense membranes, but quite interesting for membrane distillation, membrane contactors, and eventually also membrane filtration, ultrafiltration, eventually in non-aqueous solution. A lot of PVDF exist, which are not the traditional one, and depending from your understanding what you really need from your polymers, and some of you are learning how significant can be the transformation you can have in your membranes, changing the operating parameters during the extrusion, as in hollow fibers, or just by casting in a flat sheet. You can see here that all this kind of different copolymer can have a different kind of performance. You can find today in literature a lot of study on this, in this recent review that was done here at Anyang, because it seems quite interesting to try to control this performance. The utilization you saw already is quite wide. You can go from fuel cell to the previous, to the chloroalkali industry, by the way. I was mentioning already that is a very important area of operation, or to the microfiltration, membrane distillation, and everything that we have been also discussing. Keep in mind that these are the traditional ones. You can go in literature, you find already reference. There are new ones that you don't find basically any reference or few patents eventually, but very few publications. For example, this Iflon. Iflon AD, very expensive. This is a kind of polymer produced from DuPont for very special application, quite stable, and is interesting potential in gas separation and membrane distillation, membrane contactors. This is again another Teflon. Also, sorry, this is not Teflon, this is Iflon. This we discussed already. This is similar to Teflon, but they have a short branch and not long one as in Nafion, for example. This is produced basically in Europe, and the other one is produced in the United States. And some other ones are also becoming popular at this CyTop. And the difference between these different configuration is mainly not in the main chain, but in the side chain, in the branch that you can have, short, longer, etc. There are also different ways that you can utilize to prepare them, and each one of the different way of doing will give you a final different kind of membranes. So you will have to learn in the next lectures about phase inversion, which is the most utilized way of doing, and particularly you will learn that for this kind of material, phase inversion is not the traditional one, because most parts of these polymers are not soluble at room temperature in any solvent. So you have to operate at high temperature and with specific solvents. And that is what's called TIPS, thermal phase inversion, which is again a little bit more complicated than traditional phase inversion, and you have to know how does it work. And there is some motivation sometimes for changing also the form of phase inversion, not only in terms of temperature, but also in terms of mechanism to induce the phase inversion. So you will learn about the VIPs and about NIPS. That means vapor phase inversion induced or solvent. So there are different ways in which today we can realize the phase inversion, and continuously people are learning and realizing new form. For example, if you go again on the 10th floor, people are working trying to understand systems in which NIPS and TIPS work together. The final performance of your membranes are in part related to the TIPS effect and in part related to the NIPS effect. And that can change you, for example, the distribution of the final morphology of your polymer in one of the polymorphs which exist. Typical case, that is the case of some PVDF that can exist, we will see in 4 or 5 different configurations. And this different configuration can be present in your final membranes on the dense key, on the upper part, on the bottom part, in the center, and you can change the percent of this polymorph playing with NIPS, TIPS, or other kind of inversion. And there are new way of doing, for example, electrospinning, which is quite interesting because you can produce very porous material. And with very porous material, for example, in membrane distillation, electrospinning in some cases is quite interesting. Other way of doing exists, and again, you can combine, for example, the stretching, that is a normal way to induce microporosity in some material, can be also combined with normal phase inversion sometimes. You can make phase inversion under stretching and combining this kind of effect. All these things are becoming one time. Years ago, they were just art that people were learning by making a lot of experience. Today, there's a lot of understanding what has to be done. So it's no more art. You can just have much more science inducing this. And also for the important part of the story that you have to try, most parts of the membrane you are preparing, they are not ready for utilization. After having the membrane done, there will be some coating on the surface, some surface coating, some surface grafting to increase or decrease eventually hydrophobic or hydrophilic character, or to control better fouling. Blending is another way in which you can just improve mechanical properties or some other effect of your materials, etc. So this is another area in which a lot of work has to be done and understood for making better membranes. One of the areas of particular interest in which until now there was not too much attention is trying to understand at molecular level. Remember, this is the request of process intensification logic. You want to do as much as possible in the better way. What do you have in your hands? Everybody is talking about PVDF, and sometimes you just buy PVDF, or you read the publication. They say, "I'm using PVDF." PVDF exists in many different forms, as I was mentioning already. At least you can have different polymers, different polymorph of the same material. And this polymorph can be quite different. They can have different conformations. They can be linear, they can be branch, they can be polar, they can be apolar. They can be totally different. They can be piezoelectric. One of those, the beta form, is piezoelectric. That means he can applying pressure, you can induce some interesting phenomena, which can be also utilized for controlling fouling eventually. The possibility to have membranes based on PVDF totally in alpha or in beta until now was not discussed. There was no information about this, and some of you is already working trying to see if it's possible to do something similar, at least to understand how changing completely this, there's another part interesting. The alpha form is kinetically more favorable, but is not thermodynamic. The thermodynamic form is the beta, which means that if you are trying to predict on long term the aging of your membrane, if you want to have a membrane that will stay for 5 years, 7 years, running the same way, if they are not stable from a thermodynamic point of view, these membranes probably will have aging phenomena with time that you can eventually predict, and if you know what is going on, but it will not be a surprise if you understand that is. But if it's alpha, as is not beta, the problem can be different. So very important to understand which kind of this form is present in your system. And until now, as you know, these things were not really very well present. Just again to show that if you're moving from the alpha phase to the beta phase to the gamma phase, this is monoclinic, this is orthorhombic, this is non-polar, this is polar. So it's not minor difference. It can be quite significant difference, not very understood until now, and not very analyzed, and some of them can be quite important for some of the membrane application. That's why there is the interest, for example, on some of these polymer as PVDF until now in the last few years has been increasing quite significantly, and more. Here there was no mention, no one, we were not aware. We were using PVDF many years ago. I was not aware there were 5 polymorph, no idea. We have been learning just in the recent year, as you can see here, where the interest is growing. And there is nothing similar today for other polymers. If you are looking Iflon or Alar, this kind of phenomena are not yet just analyzed. Just to show you that different methods can give you quite different performance, and that is, for example, this, the VIPS, the vapor-induced phase separation, where you can see here that you can create high porous membranes with pore size in the micron, submicron range. But what is interesting is also to see how you can change the, let's see, the casting freezing methods. But, well, by the way, this is the electrospinning method. You can see here you can have these fibers that are quite interesting, very porous, and with this one you can prepare your support for some kind of material, for example, in membrane distillation or in batteries. Batteries are also using very much this one. Before going to the relationship, another aspect that I mentioned already, but I like to recall because it's becoming important, when you will study how to make TIPS, NIPS, or VIPS, what it is, you will learn that one of the most important parameters controlling all the story is the quality of the solvent you are using. So we have today a lot of information on the membranes already existing based on the kind of solvent people have been using until now. Now, if you go and you read regulations that are becoming law, most part, basically all, the solvents and diluents that people have been using and we have been using until now to prepare membranes in PVDF and similar as dimethylformamide, dimethylacetamide, NMP, or dimethyl sulfoxide, etc. All these materials that are present in our lab slowly will have to disappear, because on the basis of new regulation, REACH in Europe is the kind of rule we have to follow. Most of the solvents or diluents are toxic. So not today, they will not disappear tomorrow, but in 2, 3, 4, 5 years, they will disappear. That means if you want to predict the utilization of your membranes for much longer than the time related to the application of REACH, we have to start to study how to make these membranes with this material with new solvents, not present in this list here, and that will be available for the next 10 years, 15, 20 years before somebody will change. And this is changing completely the scenario, because we know you will learn that changing the solvents, everything is going to change. So we have to learn how to do it. That's why people are starting already to work on this line and looking, for example, again, if you know, here in Anyang, there are some of you that are working on some new kind of solvents, not yet present in the list of the solvent to be banned. This one will not be probably the best one, as the citroflax and similar, and ATCB, but these today are much more greener than the one. They are not yet listed as forbidden shortly. And that is one of the solvent that people are studying. But if you introduce this new solvent, because it's much more environmental friendly, the first thing you have to do is to start again to study all your system. Because otherwise, the membranes that you are going to be, again, an artist, making experiment on experiment, try to make control porosity, thickness, but we don't like to do anymore. So you have to start from studying the cloud points, crystallization problem, and to build up this kind of phase diagram where you just, everything about cloud point, gel transition temperature, crystallization temperature, and so you can predict that a certain concentration you can have liquid-liquid phase separation, and another concentration higher than 24%, you will have solid liquid phase separation. And if you have this different kind of concentration, the final morphology of the system will be very different. Because in one case, we know you will have a bicontinuous structure at concentration lower than 24% with this kind of solvent, and at higher than the 25, there's 25% more, you will have a spherical final morphology in the system, and this will give totally different performance. For example, the membrane pore size presents a decreasing tendency with the increase in PVDF concentration, which is related to the kind of structure that you are realizing with concentration higher than 24. And this are quite interesting difference. The pore size of the bottom surface increase with temperature because of the decrease of supercooling rate, which reduces crystallization driving force. So these parameters are 100% related to the kind of solvent you are using, and they are related to the polymer you are using, obviously, but not only to the polymer, but in phase inversion to the kind of solvent. Change the solvent, all the recipe will be different. And these are the parameters that we need for deciding if these membranes will be good for membrane distillation, for microfiltration, they will have a good level of porosity or level of mechanical properties combined. Because at the end of the story, by the way, and the other thing that you will learn to do today, not yesterday more and more, will be also to make your infrared, etc., because that will give you the percent of the beta phase and gamma phase present in your final, in your system. And now we are learning how important can be to know if it's alpha, if it's beta, if it's gamma, or what it is. Not only which is the percent, but also how it's distributed. And so you will have also technique to know if it's on the surface, in the center, in the bottom. That's why you will see more and more that for all the membranes that you are preparing, this kind of analysis is becoming interesting. Here there are some parameters that you can see how this can be affected. The mean pore size, for example, that means the size of your pore, you can see here, changing the polymer concentration, going from liquid-liquid to solid-liquid variation. You can go from 0.5 microns to 0.2 microns to 0.3 microns with a certain regularity, 15%, 20, 25, 30%, and the overall porosity is not linear with this kind of, with the change in pore size, but there is also a relationship between porosity going through a maximum related to the pore size and the mechanical properties. Here's a typical example that of the overall performance of this kind of membranes in terms of permeability. When you are making membranes, first thing you have to measure after all these infrared, etc., is transport property, otherwise not a membrane. You can see here the change in the polymer concentration, the transmembrane water flux as function of the pressure can also change significantly. You can have from 1 this is just water, so you are not expecting any fouling phenomena, etc., any problem. Everything is just related to the overall morphology of your membrane. And you can see how significant can be the effect in terms of polymer concentration or in terms of the quenching temperature. That means the temperature of the bath, where you just make the phase inversion basically on your system. So depending from this parameter, from the temperature, from 40 to 60, you can change about from 100% the transmembrane flux in the system. So all these parameters, again, they cannot be any more hard. Just the experience has to become numbers that you can predict and make your calculation and giving to the people making the production, because they have to realize 3 million square meters of these membranes to be installed in a plant that is where 3 million is necessary. And they have 3 million of the same membranes done in the same way. So no art anymore. You don't sign the production at the end, because you must be sure that this number are very well respected. And for doing this, all this relationship has to be very well known. Here's again case how you can change. Outer surface is much denser than inner surface because of diluent evaporation, and by this shrinking caused by cold water. So all these parameters are quite interesting, and they are the one that can change easily. This is our hollow fibers. This is what we call for hollow fibers. Some of you are familiar with. And in hollow fibers, you can have very different final morphology. That means very different distribution of size of the pore and distribution of the pore, depending from the temperature in which you're working, from the air gap during your coalescence phenomena and so on, which will not only affect the pore size and the overall porosity, but the mechanical properties. So that these are just all the parameters necessary. I'd just like to show you one final case, which is interesting, and this is what is happening with this new polymer that is not still not too much is in the literature. Basically, there are all 3-4 papers today in which basically that we saw already the structure. And this is interesting because there is a very different story in terms of relative speed extraction for water and for the solvent. Compared to the traditional PVDF story, we can have a realize here situation in which, by the way, with ALAR, you have to work always in tips. PVDF can be tips, that means high temperature, 160, 180, 200 degrees centigrade, and eventually, with appropriate solvents, NMP, etc., you can also make nips. With some other polymer, as this ALAR, no nips. We don't know, at the moment at least, solvent that in which these things can be dissolved. They're not existing. Eventually, some people will try to realize in the future, but today, this is a strong hydrophobic material, but totally insoluble at room temperature. So you have to operate in a situation which everything is a tips, and again, you have to start to measure again your cloud point temperature of the polymer diluent system, and to try to understand how the system works. And when you know this, you can realize interesting that you can just have quite different morphology, going from dense skin on the one side to very porous skin on the bottom side, and that is question of the different temperature you are working. And that is the level of hydrophobic character, the contact angle. You can see that basically is quite interesting, much higher than the PVDF as I was mentioning before, but it's also different between upper side and bottom side. And that is important if you learn how to reproduce it, because that can be the way for better controlling the final morphology. This effect on the roughness I was mentioned before, you can have, in this case, you can also produce symmetric membranes. You can decide if you want to have asymmetric or if you want symmetric, changing the relative velocity of extraction of the solvent from the solution. but you can have, if you want, you can have a porous symmetric morphology with the roughness of the surface top side lower than the one on the other side. And that is a special case, and you can change also significantly the level of roughness. This is the upside and bottom side we saw already before, and that is the comparison I think we saw already. That is, you can also make composite membranes from this kind. This Acurel is traditional commercial membranes in polypropylene, and you can try, with what we are trying to do, you can try to make a thin coating of this Haller on this propylene. Not easy to be realized, but that is one of the way to try to solve the problem. And this is typical configuration of these composite membranes with different time for your coatings. And the final result of this one is not very exciting at the moment. In fact, we are not just utilizing at the most. It's interesting, however, that doing this way, you can significantly tunnel. You can just mean pore size can be changed significantly. So if you want to decide to produce membranes with, in 0.5 or 0.2 or 0.1 or 0.3 microns, and depending from the time of your deep coatings with this polypropylene plus different concentration in Haller, you can just try to tunnel, and that is the final goal of this kind of work. If you want to have this control of the porosity, we saw before that can be done also changing the concentration with normal PVDF, etc. But the level of reproducibility is very low. Most part of the membrane that you buy sometime on the market today, and they tell you this is 0.5 microns or 0.2 microns pore size, measured by yourself, you will never find the same numbers, because depending from, if you are very accurate and you have a very expert person doing this, they are able to do it. But if you just go in a normal industrial production, very difficult to reproduce. For different applications, this is not very important if you are working in microfiltration, for example, so don't worry, and the people buy, they assume it's 0.2, if it's 0.1 or 0.3, nothing happened. If you are working in membrane distillation or in membrane crystallizer, that can kill your process completely. That's why you have to learn how to do these kind of things. Find the system in which you can tunnel the side having 0.5, 0.4, and trust the result that you have. Basically, these kind of results are interesting. That's again, that what you expect in a membrane distillation performance. You can see these membranes are going to be tested basically not in microfiltration, but in direct contact or vacuum membrane distillation. And this behavior, now you understand very well exactly what you expect. It's just a transmembrane flux as function of the temperature, and is not linear, because we know that in membrane distillation what we expect is an exponential behavior. That's exactly what is happening here. And you also expect that there is a difference between the two kinds of configuration, not only in terms of transmembrane flux, but in terms of overall energy consumption. Normally, you'd have less thermal boundary problems on the permeate side. And that's why this configuration is also interesting. But anyway, for the rest, they are just interesting performance at the end. Remember that you can have, in all this case, changing again the parameters we are discussing. You can have, with the same material, the same polymer, eventually the same concentration, if you like sometimes, you can have spongy with fingers at outer surface, spongy with fingers without, asymmetric. This is just symmetric system, or asymmetric with finger at inner and outer surface, or only on outer surface. This is just telling you that playing with these parameters, we can handle completely our fibers, having a system in which it can be asymmetric, can be symmetric. We can have fingers on outside or inside the pore. And that is related to the kind of system. And what is changing very much during this kind of experiment is also the level of porosity. If you have a porosity, in this case, of about 82%, 80%, this can be the best fibers today produced. Basically, they don't exist at commercial level, because if you're just going to see this porosity in terms of mechanical properties, you will find here a tensile strength of 1, 1.5, 2, which is not good enough for microfiltration for sure. In membrane distillation, we learn we don't apply any pressure. Mechanical stress is much lower, so in principle, if also this, if you can realize this level of porosity, that means increases significantly the flux, with the mechanical properties not too bad, that means instead of 3, 4, 1, 1.5, you can try to suggest the utilization of this kind of materials. And that's why people are working on this. And now if you go and to close the discussion, if you go in literature and you try to compare in the specific case of vacuum membrane distillation and direct contact membrane distillation with all the different reference you can find in literature in the years, and you see the current study with PVDF, one of the PVDF, I don't know which one it is. If you speak with your colleagues, they already learned that they have in the hands at least 6, 7 PVDF. And they will tell you that you can work with a 10-15, 60-20, 60-30, 10-10, etc. Each one of these PVDF has different properties and can give or not give good performance. The one in which people are today, we are putting more attention, is this one here, with no mention what it is. And if you look, that is the current study, and if you are looking to the performance in terms of this transmembrane flux, etc., there is a 50 that no one has in the other kind of, in the literature until now. And in terms of other performance, they are quite interesting. That's for telling that if you just try, not only, if you know what you are looking for, that means if you know that you need high level of porosity, that you need a high level of roughness in one surface more than the other, if you need a pore size, you want to have a high level of porosity, but not big pore size. Otherwise, you learn that with big pore size, there will be no hydrophobic character, because the Laplace equation is telling you that the size of the pore, if it's too high, there will be liquid penetration just for any few millimeters of water that you apply. So if you have a clear idea in mind what you're looking for, you can today try to realize with the new polymers the appropriate configuration for having the result expected. And at the end, you make membranes which are better than all the other membranes around, not just by heart, but just understanding all the mechanisms that control the final morphology of the system for the specific application. Because if you want to use this membrane not for the vacuum or direct contact, but for microfiltration, this is not necessary. Without considering that you have been learning that, for example, for all these membranes, in the moment in which you are going to analyze more in detail, for example, the power efficiency, that means how much energy you are consuming, you have been learning already that the thickness, here we have not been talking about thickness. The thickness is important because the thickness is controlling the possibility to lose energy in warming up the polymers, and if you increase a little bit the thickness, the efficiency is increasing in terms of loss of energy consumption. So all these parameters are the ones that at the end are giving you results that can make progress compared to what is already in the literature. Okay? Good. We stop here for today. Next week, we will, by the way, we will close next week. This year there is a little bit longer term, I learned, but we will have lectures on Wednesday and Friday next week, and we will not use the following week. So we will close next week, and we'll start to discuss some other process. One is the pervaporation, but the other one, membrane reactors, which is the first example of unit operation based on membrane where you have separation and, for example, chemical reaction together, as some other one we will see. But chemical membrane reactors is one of the areas becoming more and more of interest for where all these operations, microfiltration, ultrafiltration, gas separation, are integrated with traditional chemical conversion. And so they are becoming reactors based on membranes. Membrane reactors is one of the areas where more attention in biotechnology, in petrochemical industries in progress today, okay? And we will not have lectures on the week of the 18th, or what is 14, 18, and we will discuss before preparing your middle term evaluation during that week, okay? Okay, thank you.